Okay, rate of reaction. So, what do you think the rate of reaction means? Well, we could look at the word rate, and that has some type of speed associated with how fast something is occurring. And then obviously reaction, how fast a reaction's occurring. And and that's true, but how do you measure how fast a reaction's occurring? What you have to do is you have to see how quickly the reactants are being used up or how quickly the products are being formed. So the way that you would do that, well, first let's talk about it. If we're talking about how quickly reactants are being used up, how could we measure that? Well, we could measure it in the moles of reactant being used up, or we could measure it how else? Maybe in the grams of reactant being used up. Try to think in the lab, how many different ways can you actually observe a change in something? The volume, so we could look at the liters of it, how quickly that changes. And then there's a time component. So we know that we need to look at these things. I should have used a comma here. And then there's a time component. So when we look at the rate of reaction, we know that we're going to be considering, just like if you were timing somebody's 40-yard dash, you would be timing how fast that they run a certain amount of yards in a certain amount of time, yards per second. Um, in physics, you use oftentimes meters per second. And in the car, you could use miles per hour. It's important to not let units deter you from understanding the core concepts. A lot of students will get flustered when they see different letters and different types of units. But what we're really talking about here is distance over time, right? I mean, it doesn't matter which one of these you use. It all boils down to distance over time. Well, over here, it doesn't matter whether you're doing the change in moles over time, or maybe you would want to do the change in grams being used up over time. Maybe you'd want to see the change in volume over time. What we're really talking about here is a change in concentration or amount over time. How much of this chemical is being used up in the case of your reactants over time, or if you're measuring the rate of product formation, how much of this product is being formed over a certain amount of time. So it's very important to understand how we define the rate of reaction and what are some ways that you can actually do this experiment. Well, how about the vinegar and baking soda experiment? What if we wanted to study the rate of reaction on that? Well, without writing the chemical formula right, or the balanced chemical equation right now, I'm just going to go ahead and show you what a possible setup could be for that. So we could take a beaker, we could put it on a scale, and we could fill the beaker up with baking soda or baking powder, sodium hydrogen carbonate. Then we could take our timer over here, we could tear we could just measure the mass, and let's say the mass was 200.00 grams of baking soda. Well, what do you think we could do to time the reaction when we add the vinegar? What would we be looking for a change in? We're going to get a little graduated cylinder here, and it's going to have the vinegar in here ready to pour in. So what do we need here? Well, we need a stopwatch to measure when we start this thing. We got to click the stopwatch to measure the time in seconds or whatever unit you would want. So I think you get the idea here. So this is what you would do. You'd pour in the vinegar, and one of the products of this reaction, as a matter of fact, you would need to know the reaction so you could realize that the mass is going to go down, because as this reaction occurs, once you pour in the vinegar, carbon dioxide is going to be evolved. Carbon dioxide gas is going to escape this beaker, and then you'll notice the numbers on the scale going down, because this carbon dioxide gas has a certain amount of mass. And that's something that is intuitive, and it's something that's not difficult to grasp, is that, okay, well, this carbon dioxide gas, even though it would be difficult to put on a scale, we can see the mass of carbon dioxide leaving as this reaction's occurring. So then if we were to graph this, we can measure the rate of the reaction by graphing the mass here in grams, and then we would put time in seconds down here. Now, is the mass starting higher or lower? Well, right, of course. The mass, when we measure it, is going to be way up here, because 200 grams. That'd be 200. So then as this reaction's going, what do you think is going to happen? Imagine the line that's going to form here. What's going to happen is it's not going to be a straight line going down, and I'll tell you why in a second. What you're going to have is you're going to have a pretty steep line moving down. It's going to start to slope, and then eventually it will come to rest, and it won't change. Now, what do you think's the reason for the steepest slope? I want you to think about that for a second. Why would the slope taper off and become less? Why would it just flatten out and remain like this? Okay, right. The reason why it's steep in this area is because it's the point where you have the most vinegar and the most baking soda all together at the same time. So there's a lot of interaction, there's a lot of reaction going on. It's almost like in those old William Wallace movies where they're fighting, and you've got the English on one side with their horses, and you've got all the Scots on the other side with all of their kilts and all of their swords and everything. And then the movie starts out, and when is the most action-packed melee between soldiers? Right, it's right at the beginning. I mean, the movie builds up that anticipation to this point where when they meet right here, that's when things are going crazy, and all these fighting's going on, and all this, action scenes are going. But then what happens as the action scene progresses in the battle? Right, it slows down. Why? As guys are getting injured, and as the whatever side's winning, the battle begins to slow down until it's over. Sorry for the kind of wartime imagery here, but I think it does represent why the reaction is fastest. You notice we have the greatest slope, the steepest slope here at the beginning, when you have the greatest concentration of these two armies, if you will, or actually reactants meeting, and then there's really a lot of reaction going on. And then as it's used up, that means that these molecules, now we're going to call them molecules, so we don't have to imagine, people in a gruesome battle back in historic times. As these are used up, there's less and less fighting going on. There's less and less reactions going on as these molecules of reactant are gone because the product's already gone. That left. And then eventually it just tapers off and nothing happens. Why? Because the reaction is over. There's nothing else. There's no more interaction between molecules anymore because all you have is the product. So simply put, if A and B are all used up and C and D is all you have left, you're not going to have any of these reacting anymore. This is all gone. This is zero. This is all gone. This is zero. This is 100% of what's left, so the reaction is over. So it's important to understand that, and there's other ways that you can measure the rates of reactions, and it's good to just keep these in mind for any type of experimentation you want to do in the future. Another way, what's another way we could use the same chemicals and still do this? Well, you could take a flask and you could put the baking soda in here. So let's put the baking soda in the flask. And now you could have a little stopper in here with a hole going through it, and there's a tube coming out of the top of that stopper. And what you can do is you can set up this little apparatus. I won't get into it too much today, but you can basically fill a graduated cylinder within another cylinder. I don't want this to get too complex. With water. So look, now this is filled with water. Water, 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 water. You know what? Why not? Water, water, water. Yeah. Coloring is relaxing. It fills this up with water. Well, you fill this up with water. Now, what happens is you go in, you take the stopper off, and you can introduce what? I'm sorry, this should be vinegar. Or it doesn't matter, either way. Let's say this is the vinegar. Okay, and now we have a little packet of baking soda in like a little loosely wrapped piece of plastic. You take the stopper off, you drop in this other reactant. What do you think is going to happen? Right, the carbon dioxide that's being formed here is going to travel through this tube, and it's going to travel up in here. It's going to bubble up, and it's going to start to displace this water up here as the reaction progresses. And you can actually, with a timer, you can look or record, even better. Let's do the record. You can record this change in volume on the graduated cylinder that's evacuated. And of course, as you record, you'll be having a timestamp. So as it's recording, your seconds will be ticking off. 1 second, 2 seconds, maybe even have milliseconds or something. So this is going to go down as carbon dioxide forms, and then eventually what's going to happen? It's over. This is all, it stops. There's no more carbon dioxide formed. Now try to imagine what the graph of that would look like. Let's do our graph again. Now, time is here, and what would be on our y-axis this time? We're not measuring grams, but we're measuring volume. So you would say milliliters here. Okay, we're measuring the milliliters and how quickly the milliliters of gas form up here. But notice that how many milliliters of gas do we start out with at the beginning when it's filled up with water? Right, 0. So that's down here. So this graph is going to look a little bit different than the previous graph. And then what's going to happen at the beginning? Is it going to stay low and then come up over time? No, it's actually going to be steepest again at the beginning when you have the highest concentration of reactants. And then over time, it's going to gradually taper off, and taper off until it flattens out when the reaction's over. So again, the same principle applies, is that when the reactants are at their highest concentration, which would be in the beginning, you get the steepest slope, which means that the reaction's fastest at the beginning, the initial rate of reaction. And then what happens is over time it will slope off. And then what does this represent right here? This point. Right. Reaction is over. It's complete. Probably even say that's like right at the point where you have zero slope here would be the end. I hope that's helpful to understand the rate of reaction in terms of chemistry and doing experiments. One other quick way you can do this, sometimes there's a light emitting device that's emitting light into a test tube, and if your reaction changes color, then there's a detector that can sense the change in absorption or transmission, and that's just another way. But anyway, that's a good foundation. I hope this was helpful, and have a great day.